Hello, I am Jada of Jaded Company, and I will be starting Chapter 4 on operators in the complete reference of Java. Chapter 4 Operators. Java provides a rich operator environment. Most of its operators can be divided into the following four groups: arithmetic, bitwise, relational, and logical. Java also defines some additional operators that handle certain special situations. This chapter describes all of Java's operators except for the type comparison operator instance of. Instead, uh, it is which is examined in chapter 13, and the new arrow operator, which is described in chapter 15. Arithmetic operators. Arithmetic operators are used in mathematical expressions in the same way that they are used in algebra. The following table lists the arithmetic operators. Operator plus, addition, minus, subtraction, asterisk, multiplication, forward slash, division, percent, modulus, plus plus, increment, plus equals, addition assignment, minus equals, subtraction assignment, asterisk equals, multiplication assignment, forward slash equals, division assignment, percent equals, modulus assignment, and minus minus decrement. The operands of the arithmetic operators must be of a numeric type. You cannot use them on Boolean types, but you can use them on char types, since the char type in Java is essentially a subset of int. The basic arithmetic operators. The basic arithmetic operators, addition, subtraction, multiplication, and division, all behave as you would expect for all numeric types. The unary minus operator negates its single operand. The unary plus operator simply returns the value of its operand. Remember that when the division operator is applied to an integer type, there will be no fractional component attached to the result. The following simple example program demonstrates the arithmetic operators. It also illustrates the difference between floating point division and integer division. A comment. Demonstrate the basic arithmetic operators. Class, basic math, public static void main, string args, common arithmetic using integers, system.out.println, integer arithmetic, int a equals 1 plus 1, int b equals a times 3, int c equals b divided by 4, int d equals c minus a, int e equals negative d. System.out.println, quote, a equals, end quote, plus a, semicolon, end of statement. I'm not going to be saying semicolons anymore. System.out.println, quote, b equals plus b. System.out.println, c equals plus c. System.out.println, quote, d equals plus d. System.out.println, e equals plus e. Common arithmetic using doubles. System.out.println \n floating point arithmetic double dA equals 1 plus 1, double dB equals dA times 3, double dC equals dB divided by 4, double dd equals dC minus A, double dE equals negative dd. System.out.println, quote, dA equals plus dA, system.out.println, quote, dB equals plus dB, system.out.println, quote, dC plus dC, system.out.println, quote, dd equals plus dd. System.out.println, dE equals plus dE. End of program. When you run this program, you will see the following output. Integer arithmetic, a equals 2, b equals 6, c equals 1, d equals negative 1, e equals 1. Floating point arithmetic, dA equals 2.0, dB equals 6.0, dC equals 1.5, dd equals negative 0.5, dE equals 0.5. The modulus operator returns the remainder of a division operation. It can be applied to floating point types as well as integer types. The following example program demonstrates the modulus. Demonstrate the modulus operator. Class modulus. Public static void main string args. Int x equals 42. Double y equals 42.25. System.out.println x mod 10 equals plus x modulus 10. System.out.println y mod 10 equals plus y modulus 10. When you run this program, you will get the following output. X mod 10 equals 2, y mod 10 equals 2.25. Arithmetic compound assignment operators. Java provides special operators that can be used to combine an arithmetic operation with an assignment. As you probably know, statements like the following are quite common in programming. A equals A plus 4. In Java, you can rewrite this statement as shown here. A plus equals 4. This version uses the plus equals compound assignment operator. Both statements perform the same action. They increase the value of A by 4. There is another example. A equals A modulus 2, which can be expressed as A modulus equals 2. In this case, the modulus equals operator obtains the remainder of A divided by 2 and puts the result back into A. There are compound assignment operators for all of the arithmetic. Binary operators, thus, any statement of the form var equals var op expression can be written as var op equals expression. The compound assignment operators provide two benefits. First, they save you a bit of typing because they are shorthand for their equivalent long forms. Second, in some cases, they are more efficient than their equivalent long forms. For these reasons, you will often see the compound assignment operators used in professionally written Java programs. Here is a sample program that shows several op equals assignments in action. Comment: demonstrate several assignment operators. Class op equals. Public static void main string args. Int a equals 1. Int b equals 2. Int c equals 3. A plus equals 5. B times equals 4. C plus equals A times B. C percent equals 6. Modulus equals 6. Sorry. System.out.println quote A equals plus A. System.out.println B equals plus B. System.out.println C equals plus C. The output of this program is shown here. A equals 6, B equals 8, C equals 3. Increment and decrement. The plus plus and the minus minus are Java increment and decrement operators. They were introduced in Chapter 2. Here they will be discussed in detail. As you will see, they have some special properties that make them quite interesting. Let's begin by reviewing precisely what the increment and decrement operators do. The increment operator increases its operand by 1. The decrement operator decreases the operand by 1. For example, this statement, x equals x plus 1, can be rewritten like this by use of the increment operator, x plus plus. Similarly, this statement, x equals x minus 1, is equivalent to x minus minus. These operators are unique in that they can appear both in postfix form, where they follow the operand as just shown, and prefix form, where they precede the operand. In the foregoing examples, there is no difference between the prefix and postfix forms. However, when the increment and or decrement operators are part of a larger expression, then a subtle yet powerful difference between the two forms appears. In the prefix form, the operand is incremented or de-incremented before the value is obtained for use in the expression. In postfix form, the previous value is obtained for use in the expression, and then the operand is modified. For example, x equals 42, y equals plus plus x. In this case, y is set to 43, as you would expect, because the increment occurs before x is assigned to y. Thus, the line y equals plus plus x is equivalent of these two statements. X equals x plus 1, y equals x. However, when written like this, x equals 42, y equals x plus plus, the value of x is obtained before the increment operator is executed. So the value of y is 42. Of course, in both cases, x is set to 43. Here in line y equals x plus plus is the equivalent of these two statements. Y equals x equals x plus 1. The following program demonstrates the increment operator. Demonstrate plus plus. Class incdec. Public static void main string args. Int a equals 1. Int b equals 2. Int c, int d. C equals plus plus b, d equals a plus plus, c plus plus. System.out.println, quote a equals plus a, system.out.println, b equals plus b. System.out.println, c equals plus c. System.out.println, d equals plus d. The output of this program follows. A equals 2, b equals 3, c equals 4, d equals 1. The bitwise operators. Java defines several bitwise operators that can be applied to the integer types long, int, short, char, and byte. These operators act upon the individual bits of their operands. They are summarized in the following table. Tilde, tilde, bitwise unary not, and, bitwise and, bitwise or, bitwise exclusive or, shift right 0 fill, shift left, bitwise and assignment, bitwise or assignment, bitwise exclusive or assignment, shift right assignment, shift right 0 fill assignment, shift left assignment. Since the bitwise operators manipulate the bits within an integer, it's important to understand what effect such manipulations may have on a value. Specifically, it is useful to know how Java stores integer values and how it represents negative numbers. So, before continuing, let's briefly review these two topics. All of the integer types are represented by binary numbers of varying bit widths. For example, the bit value for 42 is 001011010, where each position represents a power of 2, starting with 2 to the 0 power at the rightmost bit. The next bit position to the left would be 2 to the power of 1, or 2. Continuing towards the left with 2 to the power of 2, or 4, then 8, 16, 32, and so on. So 42 has one bit set at position 1, 3, and 5. Counting from 0 at the right, thus 42 is the sum of 2 to the power of 1 plus 2 to the power of 3 plus 2 to the power of 5, which is 2 plus 8 plus 32. All of the integer types except char are signed integers. This means that they can represent negative values as well as positive ones. Java uses an encoding known as 2's complement, which means that negative numbers are represented by inverting, changing ones to zeros, and vice versa. All of the bits in a value when adding 1 to the result. For example, negative 42 is represented by inverting all of the bits in 42. 0, 0, 1, 0, 1, 0, 1, 0, which yields 1, 1, 0, 1, 0, 1, 0, 1. When adding 1, which results in 1, 1, 0, 1, 0, 1, 1, 0, or negative 42, to decode a negative number. To encode a negative number, first invert all of the bits. Then add 1. For example, negative 42 or 1, 1, 0, 1, 0, 1, 1, 0 inverted yields 0, 0, 1, 0, 1, 0, 0, 1, or 41. So when you add 1, you get 42. The reason Java and most other computer languages use 2's complement is easy to see when you consider the following of zero crossing. Consider the issue of zero crossing. Assuming a byte value 0 is represented by 0, 0, 0, 0, 0, 0, 0, 0, in 1's complement, simply inverting all of the bits creates 1, 1, 1, 1, 1, 1, 1, 1, which creates negative 0. The trouble is that negative 0 is invalid in integer math. This problem is solved by using 2's complement to represent negative values. When using 2's complement, 1 is added to the complement, providing 1, 0, 0, 0, 0, 0, 0, 0, 0. This produces a 1 bit to the far left to fit back into the byte value, resulting in the desired behavior where -0 is the same as 0. And 111, 111, 11 is the encoding for -1. Although we used a byte value in the preceding example, the same basic principle applies to all Java's integer types. Because Java uses 2's complement to store negative numbers, and because all integers are signed values in Java, applying the bitwise operators can easily produce unexpected results. For example, turning on the high-order bit will cause the resulting value to be interpreted as a negative number, whether this is what you intend or not. To avoid unpleasant surprises, just remember that the high-order bit determines the sign of an integer, no matter how that high-order bit gets set. The bitwise logical operators. The bitwise logical operators are AND, OR, XOR, and what's tilde again? NOT. The following table shows the outcome of each operation in the discussion that follows. Keep in mind that the bitwise operators are applied to each individual bit within each operand. A 0101, B 0011, A B 0111, A and B 0001, A not B 0110, A or B 0110, not A 1010. The bitwise NOT, also called the bitwise complement, the unary NOT operator, tilde, inverts all of the bits of its operand. For example, the number 42, which has the following bit pattern 001, 01, 010, becomes 1101, 0101 after the NOT operator is applied. The bitwise AND. The AND operator produces a 1 bit if both operands are also 1. A 0 is produced in all other cases. Here's an example. 00101 010 42 and 0000 1111 15 produces 0000 1010 10. The bitwise OR. The OR operator combines bits such that if either of the bits in the operand is 1, then the resultant bit is a 1, as shown here. 00101010 42 or 0000 15 equals 0010 47. The bitwise XOR. The XOR operator combines bits such that if exactly one operand is 1, then the result is 1. Otherwise, the result is 0. The following example shows the effect of the XOR operator. This example also demonstrates a useful attribute of the XOR operation. Notice how the bit pattern of 42 is inverted wherever the second operand has a 1 bit. Wherever the second operand has a 0 bit, the first operand is unchanged. You will find this properly useful when performing some types of bit multiplication. 001 01 010 42 XOR 0000 1111 results in 001 001 01 37. Using the bitwise logical operators. The following program demonstrates the bitwise logical operators. Comment. Demonstrate the bitwise logical operators. Class. Bit logic. Public static void main. String args. String binary. 0000 0001 0010 0011 0100 0101 0110 0111 0111 1000 1001 1010 1011 1100 1101 1110 1111. Int a equals 3, comment 0 plus 2 plus 1 or 0011 in binary. Int b equals 6, 42, comment 4 plus 2 plus 0, or 0, 1, 1, 0 in binary. Int c equals a or b. Int b, int d equals a and b. Int e equals a, x, or b. Int f equals not a and b, or a and not b. Int g equals not a and 0x, 0f. System.out.println, quote, a equals plus binary a. System.out.println, quote, b equals plus binary b. System.out.println, a or b equals plus binary c. System.out.println, a and b equals plus binary d. System.out.println, a, x or b, yeah, that is XOR. XOR a, XOR b, plus binary e. System.out.println, not a and b, or a and not b equals binary f. System.out.println, not a equals binary g. In this sample, a and b have bitwise. In this example, a and b have bit patterns that present all four possibilities for two binary digits: 0, 0, 0, 1, 1, 0, and 1, 1. You can see how the OR and operate on each bit by the result in C and D. The values assigned to E and F are the same and illustrate how XOR works. The string array named binary holds the human-readable binary representation of the numbers 0 through 15. In this example, the array is indexed to show the binary representation of each result. The array is constructed such that the correct string representation of a binary value n is stored in binary n. The value of not a and is ANDed with 0x0f, 000, 1111 in binary in order to reduce its value to less than 16, so it can be printed by use of the binary array. Here is the output from this program. A equals 0011, B equals 0110, A or B equals 0111, A and B equals 0, 0, 1, 0. A XOR B equals 0, 1, 0, 1. Not A and B, or A and not B equals 0, 1, 0, 1. Not A equals 1, 1, 0, 0. The left shift. The left shift operator shifts all of the bits in a value to the left a specified number of times. It has this general form: value left shift num, where num specifies the number of positions to left shift the value in value. That is, the left shift moves all of the bits in the specified value to the left by the number of bit positions specified by num. For each left shift, the high order bit is shifted out and lost, and a 0 is brought in on the right. This means that when a left shift is applied to an int operand, bits are lost once they are shifted past bit position 31. If the operand is a long, then bits are lost after the bit position 63. Java's automatic type promotions produce unexpected results when you are shifting byte and short values. As you know, byte and short values are promoted to int when an expression is evaluated. Furthermore, the result of an expression is also an int. This means that the outcome of a left shift on a byte or short value will be an int, and the bits shifted left will not be lost until they are shifted past bit position 31. Furthermore, a negative byte or short value will be sign extended when it is promoted to int. Thus, the high order bits will be filled with ones for these reasons. To perform a left shift on a byte or short implies that you must discard the high order bytes of the int result. For example, if you left shift a byte value, that value will first be promoted to int and then shifted. This means that you must discard the top 3 bytes of the result if what you want is the result of a shifted byte value. The easiest way to do this is to simply cast the result back into a byte. The following program demonstrates this concept. Comment: left shifting a byte value. Classic byte shift. Public static void main string args. Byte A equals 64, B. Int I equals A left shift 2, B equals byte A left shift 2. System.out.println original value of A plus A. System.out.println I and B, I plus I plus system.out.println I and B plus I plus space plus B. The output generated by this program is shown here. Original value of A, 64. I and B, 256, 0. Since A is promoted to int for the purposes of evaluation, left shifting the value 64, 0, 1, 0, 0, 0, 0, 0, 0 twice results in I containing the value 256. 1, 0, 0, 0, 0, 0, 0, 0, 0. However, the value in B contains 0. After the shift, the lower order byte is now 0. It's only one bit that has been shifted out. Since each left shift has the effect of doubling the original value, programmers frequently use this fact as an efficient alternative to multiplying by 2. But you need to watch out. If you shift a 1 bit to the high order position, bit 31 or 63, the value will become negative. The following program illustrates this point. Comment: left shifting as a quick way to multiply by 2. Class multi by 2. Public static void main string args. Int I, int num equals 0x ffe for I equals 0, I less than 4, I plus plus, num equals num left shift 1. System.out.println num. The program generates the following output: 536870908 10737418116 2147483 negative 32. The starting value was carefully chosen so that after being shifted left 4-bit positions, it would produce negative 32. As you can see, when a 1 bit is shifted into bit 31, the number is interpreted as negative. The right shift. The right shift operator shifts all of the bits in the value to the right a specified number of times. Its general form is shown here. Value, right shift, num. The num specifies the number of positions to the right shift. The value in value. That is, the right shift moves all of the bits in the specified value to the right the number of bit positions specified by num. The following code fragment shifts the value 32 to the right by 2 positions, resulting in A being set to 8. Int A equals 32. A equals A right shift 2 A now contains 8. When a value has bits that are shifted off, those bits are lost. For example, the next code fragment shifts the value 35 to the right 2 positions, which causes the 2 lower order bits to be lost, resulting again in A being set to 8. Int A equals 35, A equals A, right shift 2, comment A contains 8. Looking at the same operation in binary shows more clearly how this happens. 0, 0, 1, 0, 0, 0, 1, 1, 35, right shift 2, 0, 0, 0, 0, 1, 0, 0, 0, 8. Each time you right shift a value right, it divides that value by 2 and discards any remainder. In some cases, you can take advantage of this for high performance integer division by 2. When you are shifting right, the top leftmost bit exposes by the right shift are filled with the previous contents of the top bit. This is called sign extension and serves to preserve the sign of negative numbers. When you shift them right, for example, -8 right shift 1 is -4, which in binary is 1, 1, 1, 1, 1, 0, 0, 0, -8, right shift 1, 1, 1, 1, 1, 1, 1, 0, 0, -4. It is interesting to note that if you shift -1 right, the result always remains -1, since sign extension keeps bringing in more ones in the right order bits. Sometimes it's not desirable to sign extend values when you are shifting them to the right. For example, the following program converts a byte value to its hexadecimal string representation. Notice that the shifted value is masked by ANDing it with 0x0f to discard any sign extended bits so that the value can be used as an index into the array of hexadecimal characters. Masking sign extensions. Class hexbyte. Static public void main string args char hex 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Byte B equals byte 0xF1. System.out.println quote B equals 0x plus hex B right shift 4 and 0x0f plus hex B and 0x0f. Here is the output of this program. B equals 0x f1. The unsigned right shift. As you have seen, the right shift operator automatically fills the high order bit with its previous contents each time a shift occurs. This preserves the sign of the value. However, sometimes this is undesirable. For example, if you are shifting something that does not represent a numeric value, you may not want sign extension to take place. This situation is common. When you are working with pixel-based values and graphics, in these cases, you will generally want to shift a 0 into the high order bit no matter what its initial value was. This is known as an unsigned shift. To accomplish this, you will use Java's unsigned shift-right operator, which always shifts zeros into the high-order bit. The following code fragment demonstrates the zero right shift. Here, A is set to -1, which sets all 32 bits to 1 in binary. This value is then shifted right 24 bits, filling the top 24 bits with zeros, ignoring normal sign extension. This sets A to 255. Here is the same operation in binary form to further illustrate what is happening. I am not going to read the code from this point forward. The right shift operator is often not as useful as you might like, since it is only meaningful for 32 and 64-bit values. Remember, smaller values are automatically promoted to int in expressions. This means that sign extension occurs when and that the shift will take place on a 32-bit rather than on an 8 or 16-bit value. That is, one might expect an unsigned right shift on a byte value to zero fill beginning at bit 7, but this is not the case, since it is a 32-bit value that is actually being shifted. The following program demonstrates this effect. The following output of this program shows how the zero right shift operator appears to do nothing when dealing with bytes. The variable b is set to an arbitrary negative byte value for this demonstration. Then c is assigned the byte value of b shifted right by 4, which is 0xff. because of the expected sign extension. When D is assigned the byte value of B unsigned, shifted right by 4, which you might have expected to be 0x0f, but is actually 0xff because of the sign extension that happened when B was promoted to int before the shift. The last expression sets E to the byte value of B masked to 8 bits. Using the AND operator, then shifted right by 4, which produces the expected value of 0x0f. Notice that the unsigned shift right operator was not used for D. Since the state of the sign bit after the AND was known, bitwise operator compound assignments. All of the binary bitwise operators have a compound form similar to that of the algebraic operators, which combines the assignment with the bitwise operation. For example, the following two statements, which shift the value in A right by 4 bits, are equivalent. Likewise, the following two statements, which result in A being assigned the bitwise expression A or B, or are equivalent. The following program creates a few integer variables and then uses compound bitwise operator assignments to manipulate the variables. The output of this program is shown here. Rational operators. The rational operators determine the relationship that one operand has to the other. Specifically, they determine equality and ordering. The relational operators are shown here. Equal to, not equal to, greater than, less than, greater than or equal to, less than or equal to. The outcome of these operations is a Boolean value. The relational operators are most frequently used in the expression that control the if statement and the various loop statements. Any type in Java, including integers, floating point numbers, characters, and booleans, can be compared using the equivalent test equals and the inequality test not equals. Notice that in Java, equality is denoted with two equal signs, not the same. Two equal signs, not one. Remember, a single equal sign is the assignment operator. Only numeric types can be compared using the ordering operations. The ordering operators. That is, only integer, floating point, and character operands may be compared to see which is greater or less than the other. As stated, the result produced by a relational operator is a Boolean value. For example, the following code fragment is perfectly valid. Int a equals 4, int b equals 1, Boolean c equals a less than b. In this case, the result of AB, which is false, is stored in E. If you are coming from C/C++ background, please note the following in C/C++. These types of statements are very common. In Java, these statements must be written like this. The reason is that Java does not define true and false in the same way C or C++ in C/C++. True is any non-zero value and false is 0. In Java, true and false are non-numeric values that do not relate to 0 or non-zero. Therefore, to test for 0 or non-zero, you must explicitly employ one or more of the rational operators. Boolean logical operators. The Boolean logical operators shown here operate only on Boolean operands. All of the binary logical operators combine two Boolean values to form a resultant Boolean value. Logical AND, logical OR, logical XOR, shorthand circuit or short circuit OR, short circuit AND, logical unary NOT, and assignment or assignment, XOR assignment, equal to, not equal to, ternary if then else. The logical Boolean operators AND, OR, and XOR operate on Boolean values in the same way that they operate on bits of an integer. The logical NOT operator inverts the Boolean state. Not true equals false, and not false equals true. The following table shows the effect of each logical operation. A, false, true, B, false, false, true, true. A or B, false, true, true, true. A and B, false, 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 true. A, XOR, false, true, true, false. Not A, true, false, true, false. Here is a program that is almost the same as the bit logic example shown earlier, but it operates on Boolean logic values instead of binary bits. After running this program, you will see that the same logical rules apply to Boolean values as they did to bits. As you can see from the following output, the string representation of a Java Boolean value is one of the literal values true or false? Short-circuit logical operators. Java provides two interesting Boolean operators not found in some other computer languages. These are secondary versions of the Boolean and or operators, and are commonly known as short-circuit logical operators. As you can see from the preceding table, the OR operator results in true and the OR operator results in true when A is true, no matter what B is. Similarly, and B operator Similarly, the AND operator results in false when A is false, no matter what B is. If you use the short circuit OR and short circuit AND, rather than the OR and forms of these operators, Java will not bother to evaluate the right-hand operand when the outcome of the expression can be determined by the left operand alone. This is very useful when the right operand depends on the value of the left one in order to function properly. For example, the following code fragment shows how you can take advantage of short-circuit logical evaluation to be sure that a division operation will be valid before evaluating it. Since the short-circuit form of AND is used, there is no risk of causing a runtime exception when daemon is 0. Denum is 0. If this line of code were written using the single AND version of AND, both sides would be evaluated using a runtime expression when denum is 0. It is standard practice to use the short-circuit form of and or in cases involving Boolean logic, leaving the single character versions exclusively for bitwise operations. However, there are exceptions to this rule. For example, consider the following statement. Here, using a single AND ensures that the increment operation will be applied to E whether C is equal to 1 or not. Note, the formal specification for Java refers to the short-circuit operators as the conditional and conditional or. The assignment operator. You have been using the assignment operator since Chapter 2. Now it is time to take a formal look at it. The assignment operator is the single equal sign. The assignment operator works in Java much as it does in any other computer language. It is general form var equals expression. Here, the type of var must be compatible with the type of expression. The assignment operator does have one interesting attribute that you may not be familiar with. It allows you to create a chain of assignments. For example, consider this fragment. Int x, y, z, x equals y equals z equals 100. Set x, y, z to 100. This fragment sets the variables x, y, and z to 100 using a single statement. This works because the equals is an operator that yields the value of the right-hand expression. Thus, the value of z equals 100 is 100, which is assigned to y, which is in turn assigned to x, using a chain of assignment. This is Using a chain of assignment is an easy way to set a group of variables to a common value. The question operator. Java indicates a special ternary three-way operator that can replace certain types of if-then-else statements. This operator is the question. It can seem somewhat confusing at first, but the question can be used very effectively once mastered. The question has its general form. Expression 1, expression 2. Actually, what's the name of the question mark? Ternary. Expression 1 ternary, expression 2, expression 3. Here, expression 1 can be any expression that evaluates to a Boolean value. If expression 1 is true, then expression 2 is evaluated. Otherwise, expression 3 is evaluated. The result of the ternary operation is that of the expression evaluated. Both expression 2 and expression 3 are required to return the same or comparable type, which can't be void. Here is an example of the way that the ternary is employed. Ratio equals denom equals 0, tertiary 0, num divided by denom. When Java evaluates this assignment expression, it first looks at the expression to the left of the question mark. If denom equals 0, then the expression between the question mark and the colon is evaluated and used as the value for the entire tertiary expression. If denom does not equal 0, then the expression after the colon is evaluated and used for the value of the entire tertiary expression. The result produced by the ternary operator is then assigned to ratio. Here is a program that demonstrates ternary operator. It uses it to obtain the obsolete value of a variable. The output generated by this program is shown here. Operator precedence. Table 4.1 shows the order of precedence for Java operators. from highest to lowest. Operators in the same row are equal in precedence. In binary operations, the order of evaluation is left to right, except for assignment, which evaluates right to left. Although they are technically separators, the brackets, parentheses, and period can also act like operators. In that capacity they would have the highest precedence. Also notice the arrow operator. It was added in JDK8 and is used in lambda expressions. Using parentheses. Parentheses raise the precedence of the operators that are inside them. This is often necessary to obtain the result you desire. For example, consider the following expression. This expression first adds 3 to B and then shifts A right by that result. That is, the expression can be rewritten using redundant parentheses like this. However, if you want to first shift A right by B positions and then add 3 to that result, you will need to parenthesize the expression like this. In addition to altering the normal precedence of an operator, parentheses can sometimes be used to help clarify the meaning of an expression. For anyone reading your code, a complicated expression can be difficult to understand. Adding redundant but clarifying parentheses to complex expressions can help prevent confusion later. For example, which of the following expressions is easier to read? One other point, parentheses, redundant or not, do not degrade the performance of your program. Therefore, adding parentheses to reduce ambiguity does not negatively affect your program.